Yeah, so the topic that I'm sharing today is related to construction, automation, and robotics. Especially, I summarize the research needs and also my group's research focus in the past 6, 7 years as embodied spatial intelligence. And I will try to make the connection between the two topics. Before going into the details, let me very briefly introduce my lab, AI Force. The lab's mission is to address the following challenge in the field, which is to develop novel algorithms and systems for intelligent agents to accurately and efficiently understand and interact with materials and humans in dynamic and unstructured environments. We believe this is the sort of like the fundamental research need in this field of construction, automation, and robotics before we can make technologies in this field really useful at a large scale. So in order to achieve this mission, we need to adopt the so-called multidisciplinary research methodology and adopt the so-called user-inspired research paradigm. In order to achieve such methodologies, we need expertise from multidisciplinary team. So in my group, we have students working both in fundamental robotics and AI fields such as computer vision, robotics, machine learning. More specifically, we focus on visual or LiDAR-based localization, mapping, navigation, 3D vision or perception, and learning. In the problem domain that we focus on, we're mainly interested in problems originates from the construction or manufacturing field, as well as smart cities. So that means transportation, connected and autonomous vehicle. So we mentioned today's main theme is about construction, automation, and robotics. And there is a strong need in this whole field globally, right? I'm sure the colleagues in China will notice this this shift recently. So basically, we said in the society there are two important sort of problems faced by the construction sector. And for those of you who have been in the construction field for years, you would not be unfamiliar with the following two figures that I'm showing. One of them demonstrates the high injuries and fatalities in the construction side. So here is a figure from the US, but I think the same figure or the same trend pretty much applies to every country worldwide. So it basically shows that construction typically has the highest, largest number of occupational injuries as compared to different industry sectors, right? Not only the absolute number, but also the rate is also quite significant. We also know that construction has always been accused of having stagnant labor productivity. So if you compare the labor productivity of construction versus all other non-farm industries in the past several decades, right, almost 100 years, the labor productivity of construction, no matter how you like calculate the index, different kinds of index, you always get this stagnant curve as compared to the rising curve in other non-farm industry. So we said there is this strong need or demands for bringing new technology into construction to address these two important problems. And this is not the only two problems that are faced by construction. We're also facing by issues of lack of young talents, aspirational young generations. They do not tend to think of construction industry as something as a rewarding field. So not many people are willing to enter this field. So how do we address all these as a whole? Of course, there are different ways to address it. one of the many ways that we can do and we can try to bring, and is also my personal and my group's research focus, is try to look at the high technology, right? The automation and robotics. Can we learn from manufacturing or transportation fields that has already significantly benefited from high tech, especially robotics, right? Companies like Tesla and Google, they have been attracting some of the really bright new talents into their fields by their robotic factory and self-driving cars. But besides making this analogy between construction and manufacturing or transportation, I want to point out several unique challenges for construction and robotics. So unlike manufacturing, construction environments are usually structured and dynamic. And unlike self-driving cars, the construction robots have to perform more materials manipulation, and they have to typically collaborate with human workers on the site. So fundamental research are required for construction robots. We cannot just think about applying existing techniques in automation and robotics or machine learning or even AI to magically solve problems that we face in construction and engineering management. So let me illustrate some of the more specific technical challenges faced by construction folks when we try to bring automation and robotics onto the site. So one of the first one is the so-called constantly changing job sites, right? So this is a data set that is and a challenge hosted by Stanford civil engineering department. They call this as nothing stands still challenge, right? So basically they go to some construction job site and scan in 3D very detailedly almost every week. And then you notice the site, nothing stands still in a construction site, right? The things change every week, if not every day. And this brings a lot of challenge to robotics, as we will discuss later. And another thing for specific to construction is that you typically face great difficulties in localizing and navigating agents including autonomous equipment or even construction workers. Because a lot of the construction site, when it is being built, it's featureless. It has many repetitive structures, and it is difficult for even human to know where they are if they're not familiar with the site, and especially when the site gets large and complicated. Last but not least, just like in transportation, in self-driving cars, construction site also face this severe occlusion and data sparsity issue. So if the construction equipment are observing something from far away, the number of data points you can get from either a LiDAR scanner or a camera is limited. You only have limited pixels focusing on a particular distant object, or you have limited LiDAR points focused on that object, right? So not to mention the heavy occlusion. We all know when you deal with crane operations, or like really complex confined space in a mega site, occlusion is another issue where you constantly need to check whether things are going to collide with each other or not. And especially if you're going to bring autonomous or semi-autonomous equipment like trucks, excavators, cranes that needs to operate on its own into this kind of complex site with heavy occlusion, this is even more problematic, right? So not to mention we want to use this technique to make the site more safe. Now, if you cannot address these technical challenges, you're actually bringing more danger into the construction site. So basically, we're saying construction vehicles are becoming autonomous these days. As you can see on the image here, this is not just happening in the academia. It's happening in the field, in those heavy equipment manufacturers. Companies like Volvo, Boston Dynamics, different kind of like construction heavy equipment manufacturers. Even in China, I know companies like Xugong and Sanyi Zhonggong, they are all investing in this autonomous equipment technology, right? So basically, in robotics term, we can call these construction vehicles or equipments as mobile manipulators. These mobile manipulators needs to finish one task, regardless of different specific construction jobs they have to perform. From a fundamental robotics perspective, they all need to perform simultaneous navigation and environment modification. So they need to move in order to perform their jobs. Unlike in manufacturing side, you can rarely have a robotic arm that's fixed at one place and just do work waiting for things to be transported to the vicinity of that arm. The robot actually has to go around, move around, and while they're moving around, they have to make modifications of their environment. So this is what we call as mobile manipulator in robotics. And this is an active research field, even in robotics, with rising interest because it has fundamental challenges. It is challenging the existing theories and algorithms for perception, for localization, for planning, for control and coordination. So on the left-hand side, I show this kids, like a very famous kid storybook called Mighty Mighty Construction Site, right? So if you notice on this storybook, it is basically highlighting a vision or a future that we may want to see, where you have all the equipments becoming autonomous and they collaborate coherently with each other. Is there any question? By the way, if there is any question, feel free to unmute yourself and ask, interrupt me at any time, or you can always type in the chat. Okay? All right. Anyway, so in my past research, I tend to call these mobile manipulators as WALLYs. It's just because they are more widely known to the general public, to people who are not in this field of robotics. If you talk about WALLY, people immediately get the idea. So how do we make these WALLYs safer and more efficient when we try to bring them onto a construction site? Well, the fundamental research that I believe is needed is called embodied spatial intelligence. This is a term that I coined that combines two very popular terms nowadays, embodied intelligence, or in Chinese, 具身智能, and spatial intelligence, or in Chinese, 空间智能. So it's embodied spatial intelligence. We think that this is the secret sauce to fundamentally enable construction automation and robotics, right? So what I mean by embodied spatial intelligence? Well, fundamentally, we need to understand and interact with the space that we reside in. And importantly, we need to form this kind of understanding and interaction through physical actions. We're not just doing things in an imaginary world or in a digital virtual world, such as being only, right? In order to achieve embodied spatial intelligence, you actually, your equipment, your vehicles, they move, they work in a real job site. And this is not something that is actually special or unique to construction. They reside in Mother Nature, as you can see on these figures. Many animals that you see in the cities, they have this, or even wild, they have this capability. They know how and where to find food. They know how to, for example, very interestingly, if you ever visit cities in the North America, you'll notice this kind of squirrels living in the city, and they learn to cross roads with certain level of safety, right? So they can avoid being hit by a car. This is very, very interesting phenomenon. And recently there is a PNAS journal published a work that compares this collaborative intelligence in ants versus human. And the task they give the ants is to move this structure across some kind of like interesting geometry, right? And imagine, actually, and they did this test with human workers as well, in order to collaboratively move this object, this red object, through this confined space with geometric obstacles. Even human needs to try multiple times, and we are not, believe it or not, we are not more efficient than ants, right? So this is very interesting. But most importantly, to the interest of construction folks, we want to engineer those capabilities back in machines. So not only do we want to achieve autonomous vehicles or autonomous delivery systems, material handling systems, we want them also to be able to interact and move objects, work in factories and construction sites. Now, talking about this, you probably will think, how far are we from engineering such intelligence, given all the great excitement and the progress in the field, broad field of AI, artificial intelligence. Especially yesterday, the GPT-5 is released, right? So here I want to quote from some famous experts that are known to the general public. Here, this figure shows John von Neumann, a very famous, like, believed to be the father of modern computers, right? So in not like this is almost 100 years ago, and he said, if you will tell me precisely what it is that a machine cannot do, then I can always make a machine which will do just that, right? This is almost 100 years ago, and think about what we can do now and what we cannot do now, right? There's still so many things that I can precisely tell you what I wanted to be able to do, but we cannot. For example, a machine that can do household jobs for us, or a machine that can construct. So this is another very famous scholar, a Turing awardee, and also who won Nobel Prize later. His name is Herbert Simon. He was a professor at Carnegie Mellon University, right? So he once said, 1965, that machines will be capable within 20 years of doing any work a man can do. And clearly we know that is not true even nowadays, right? And one more very famous guy in artificial intelligence, Professor Marvin Minsky, who also won his Turing Award in 1969. And he said 1 year later, after he got his Turing Award, he said, in from 3 to 8 years, we would have a machine with the general intelligence of an average human being. And are we there yet? Clearly not. So the reason I'm showing these quotes from these famous people is that, first, it is very difficult to make this kind of predictions, even by some of the brightest minds in the human history. And it also shows this field has so much potential for young and aspirational minds like you guys to join this field. There are so many interesting things to work on, and let's work on these together. So from my lab's perspective, or personally, what I think are the keys to address embodied spatial intelligence that will eventually lead to construction automation and robotics is the following 4 M's that I summarized. They are mapping, moving, making, and mingling. So I'm going to very quickly explain what these 4 words means before diving into the details. So mapping really means representing the world. How do robots build maps, or basically a representation of its surrounding environments? This means a robot has to use what we call as egocentric observations. They're not necessarily just depending on cameras or sensors installed in the environment. They have to rely on sensors installed on their body that can move together while they're moving, to representations of the observed environment. So this is what we call as mapping. And as the some of the animation figure shows in this slide that highlights my group's work, mapping, well, the most well-known mapping are metric mapping. The idea is to get accurate geometry so that you can measure distance, angle, volume, and all those things in that map. Mapping is not just metric. It also requires topology understanding. So the topological mapping is another very important form of maps. And mapping is not just about parsing the data that we observe. It's also about reasoning in those kind of complex environments. Okay. So the second keyword is moving. So we need to teach robots how to decide where to go, because if they cannot do this, then basically the whole WALL-E story, or the mobile manipulation hope that we hope the construction robots can do will not be possible, right? So in order to enable robots to decide where to go, one of the most fundamental problem is localization. They need to understand where they are in a complex 3D or 2D, simplified 2D environments. And they need to know more than that. So even if you know precisely, as shown here in this figure, which is from our group's very recent work that achieves state-of-the-art 6DoF localization of a camera in 6D. So that means we know both 3D position of the camera and also the orientation in that space from only camera images without requiring any GPS or any other sensors. So even if you know this, it is not enough for a robot to navigate in those complex environments. The robot could be a self-driving car. It could also be an excavator on a job site, right? So they need to understand the situation that the surrounding situation. What is happening? Is there any signal that prevents me from doing certain actions? When can I move across this field in front of me, and when can I not? So all these are beyond localization. They're decision-making problems. Of course, the things that are most interesting and most useful to construction folks are the making part, right? We actually need to enable these autonomous machines to build in physical world instead of, in addition to localize and move themselves like self-driving cars do. They actually need to move and do things and make things happen, right? So here make some, so the animation is from the well-known WALL-E movie. I'm sure many of you or your kids have watched this before. But I want to remind you the amazing capability by the Mother Nature. So here is a termite mound that people found in Africa, right? And I'm sure you can find similar structures in other parts of the world. So if you think about animal architects, this includes termites, but beyond termites, right? They can build structures. This is an amazing capability. Even nowadays, after thousands years of technology update in construction, we still don't have an autonomous system that can do this kind of quote unquote simple task that even a termite or ant can do, right? So that means there are some theoretical challenge fundamentally lies beneath these applications. So a couple of years ago, we actually greatly simplified these construction problem in a very theoretical and non-realistic manner for us to study what is the theoretical challenge of doing construction by mobile agents. And we simplified things in a grid-like environment, just like the Go game, right? So we know a couple of years ago, Google was able to do this AlphaGo AI that can perform super well. They can win the human champion of the Go game. So if you try to study the mobile construction problem as in a grid world, then you will be facing something like this. Even though this is already abstract out a lot of the realistic real world construction challenges, it is already showing in this simplified environment, there's still theoretical challenge, and that challenge is what we call as POM-DP for those who are interested in theory, or partial observable and Markov decision problem. So when you're facing the POM-DP problem, then of course the theoreticians will know this is a super hard, super challenging problem, even for pure roboticists or machine learning AI researchers. So no wonder construction robotics and construction automation remains one of the biggest challenge for robotics. Okay, so we're also showing some of the figures here that we try to use engineering tricks to circumvent some of these theoretical challenges. For example, on the top, we're showing a mobile 3D printing platform that my team developed to enable the 3D printing beyond a gantry-based system that you typically see either in a tabletop plastics 3D printer or on the construction side, a concrete 3D printer. Currently, they almost always depends on the so-called gantry-based system or a fixed robot arm to deliver the material. But we think if you can move this printhead onto a mobile robot and let mobile robots collaborate on the construction side, then you can essentially print much faster in a collaborative manner, and you can print something bigger than the printer itself. On the bottom, we're showing a construction like the terrain grading, autonomous terrain grading experiments happening in our lab. This is an ongoing project that we're hoping to, by researching this kind of topics, will one day enable robots to go to extraterrestrial conditions like moons or Mars to build bases for us. Right? So this is the making part. And the last keyword is mingling. This really means multi-agent collaboration. So in Mother Nature, we see all kinds of collaboration among different agents. This is an example of monkeys. They talk to each other through their way, and they communicate with each other to tell people where foods are, to tell monkeys where foods are and where the other dangers may happen, right? And this is, of course, more than just the monkeys. We see these behaviors in ants, we see these behaviors in birds, many animals, right? So this inspires us to think, how can we enable autonomous agents like robots or construction equipment to work together so they can see and act better, right? So my group has actually pioneered in this direction and developed a research subfield called co-perception or collaborative or cooperative perception. Okay, so due to the lack of needs due to the lack of data in construction side, we started by collaborating with researchers in transportation. So in transportation, we already have this kind of possibilities to either simulate or collect real-world multi-agent interaction data where you have vehicles nearby each other and they all equipped with sensors and they can talk and communicate with each other. So essentially, if you allow these agents to share what they see with each other, then collectively they see further, they see better, they see through occlusions, right? So this will make the whole system fundamentally safer than the single agent perception system. And of course, we want to go beyond just the collaborative perception. We want to, when we are bringing this onto construction sites, we want them to be able to collaboratively build, as previously shown, the two mobile robots performing 3D printing tasks together. eventually we want these robots to collaborate just like how we are doing now with humans and construction equipment. They need to collectively, collaboratively complete construction tasks together, right? So I know that we have about 40 minutes in terms of the presentation. So I actually have more details for any one of these, any of these keywords. Depending on the audience interest, I can go deeper into any one of them. But maybe in the interest of time, because Professor Mao told me that I should finish this in about 40 minutes, so that we have.
You don't worry about that. You can give more detail for this.
Okay, yeah, not a problem. So then I will have a lot more time then. I will still have about 20 minutes, so I can go into more details. And really depends on the interest of the audience. I can go faster or slower in any one of those topics. All right, so maybe let me talk about the mapping first. So for many of colleagues working in the FEM engineering management, you're not unfamiliar with the term point cloud. Many times you actually need to go out to your job site and take your favorite laser scanners, terrestrial laser scanners, sit on a tripod and let it scan the environment at different locations of the job site, and eventually you need to perform this registration task, which is what we call as mapping or point cloud mapping. And this is the mathematical summarization of the mapping problem, the point cloud mapping problem. You don't really need to worry about, I don't want to put you into sleep at a Saturday night, but what I want you to know is this problem is not unique to construction. Even in autonomous driving, we need to solve the exact same problem where you have the cars moving around in the city, and eventually they scan the local geometry at their own pose at different time, and eventually they need to take all these scans together and build a map of the entire city. This is of no difference as a construction site point cloud registration problem, okay? So in the mapping part, my groups have done some work that try to make this process more efficient and less labor intensive, even though I know this field has grown rapidly, and with the latest service or software that you may get from companies like Leica or Trimble, the process is already much more smooth than before. But still, if you're talking about scanning a site and giving all the data to the software and let it to automatically register all the point clouds without any human interference or any human attendance, I believe we still cannot do that 100% nowadays. You may always run into issues here and where that requires some human attendance, right? So in order to make this whole thing as autonomous as possible, because again, as construction engineers or project managers, we don't really care about the fundamental technology. What we want is a fast scan and understanding of the current status of the job sites and do any quantitative work as soon as possible. So basically, we developed this work called deep mapping, that is one of the most accurate metric mapping system, and it can take all the point clouds you scan, no matter whether this is done by our autonomous driving car or a job site scanning robots, and it will autonomously register. As you see here, we're plotting the sensor pose in each frame, and this is a CT scale scan, and it will automatically register all the pose that eventually aligns and very accurately. And here, this sensor pose shows the structure of a street of a city, right? So you see it from the beginning, it is very noisy, and eventually the system converges without any human attendance at a CT scale autonomously. And here shows both the trajectory of the sensor and the scanned laser points projected onto a 2D plane. And we show that our system is very close to the ground truth that is very like the high accuracy ground truth that requires even some human attendance to build. So in the interest of time, I will skip the technical details. Again, I don't want to put you to sleep at a Saturday evening. So the important thing is we developed a AI system, or basically a deep neural network, and we make this problem equivalent to training that deep neural network. So by training that deep neural network, the problem gets solved. So we don't even need to deploy this trained neural network later. Just by training the network itself, this process is equivalent to the mapping problem. And then we can leverage all the good technique in AI to make this problem autonomous. Okay? So we can do mapping not only from point clouds, but also from images. This typically is lower cost because laser scanners are still pretty expensive, and they're often bulky and heavy. If you have a pocket camera like your cell phone or a 360 camera, you can very easily walk around in the job site, and then you wonder if you can build a map from those images. And this is a very well-known problem called structure from motion problem in computer vision and robotics. In robotics, we call this as visual slant. So there are different ways people perform the traditional SFM, or more recently, people use neural network to do learning-based metric mapping or learning-based topological mapping. And here, just for those who have a mind of a theoretician, you may be interested in this very abstract mathematical form that summarizes all the mapping from images problems. But for practitioners, here are something that may be of interest to you. This is a work that we published 2 years ago at CVPR, one of the top AI conferences, of something named VoxFormer, which is a camera-based 3D semantic scene completion problem. It is originally popularized by the company Tesla in the year of 2022. And then basically what this problem is, it is that when we have a camera moving in the environment, we want to develop some kind of like end-to-end learning-based AI system that will generate this kind of what we call as voxel-like representation of the environment, which not only tells me the occupied space versus free space in high accuracy in the 3D world, but also it can tell me what things are. These different color codes are showing different part of this environment, the road surface, the vehicles and buildings, right? So this is a very interesting and challenging problem, and we were able to achieve the SOTA at that time by developing a novel transformer-based neural network architecture that generate results from this single view image into this kind of result that matches very closely to the ground truth data, whereas the previous baselines all make more mistakes. Okay. So we can also go beyond metric mapping, as I mentioned. The multi-view scene graph work that our group published last year is a representation of the so-called topological scene representation. And the reason that we want to develop methods in addition to metric mapping is the metric mapping. For those of you who have used terrestrial laser scanners, you would know if the scene changed, or if the scene changed during your scan, it can create a lot of problems, not only to the registration of multiple point cloud scans, but also it brings problems of recognition, like later on you need to figure out where this thing is, and which thing happens first and last, and how to put a new scan, how to register a new scan into the existing scan where the scene has already changed significantly. So if we move beyond the metric mapping requirement, which requires us to build a global map that is metrically accurate everywhere, we can relax that condition by saying we just need to build a graph or that preserves the topological connectivity information among those images or the objects in those images. Then we can more quickly and easily maintain such a graph even if there are changes in the environment. Because if there are any changes in the environment, we just need to replace that image and remove the corresponding object node and replace it with the new image and the new object inside it, right? So this is the fundamental idea of the topological representation beyond the metric mapping. And this kind of representation will be super useful for tasks like asset management. For those of you who have managed mega projects, you would know how challenging it could be if the job site's assets are not properly managed. You would constantly face problems of the need of finding a particular useful and unique asset, where it is and who used it in the last. And we believe this kind of topological mapping is a very flexible and robust way of addressing that problem. And here are just some of the applications that can be enabled by this kind of topological map. For example, the embodied question and answering problem application of the topological maps is a great example of resolving the asset management challenge. When you build such a topological map of the environment from the videos, the surveillance video you have of the site, then you can basically, just like how you interact with GPT, you can ask questions to such a model. Where is which object? What is the time you see that object in the last place, right? What's the last time you see that object? And I will skip the technical details, how we implement such an AI system that can do this. But I want to move on to the next keyword, the moving, with a bit more details. So we say a robot, we want to teach a robot how to move, or basically how to navigate an environment. One example that can be useful for construction, especially in the operational phase, not in the construction phase, is the exploration problem. Or the problem basically says, in the new environment that the robot has never been to before, how do you autonomously navigate this robot so that it can explore every single aspect of this environment without human attendance? Again, if a building manager, when they first taking charge of a building, they basically, if they can just send a robot dog that autonomous go everywhere, then they can leverage the information scanned or collected by this robot to build the maps that we talked before. But before that, you have to solve the problem of how to tell the robot to go to all the places in this building. Because remember, this is a new place that this robot has never been to before, and you don't have a map, right? So maybe you have a beam, but the beam never has the actual condition. They're always as designed. The as-built beam, as far as I know, is still far from being implemented in the real world. And even if they're implemented, they don't have the real world conditions. You don't have the real world texture, real world details. So it will still be good for a robot to be able to autonomously navigate and explore such an environment without missing any key places. So this slide, we're showing something called Deep Explorer that we published again 2 years ago in a top robotics conference called RSS, Robotic System and Sciences, where we enable this robot equipped with only one 360 camera. So this image you see are the equirectangular images that are captured by a 360 camera. So basically you get the surround view very easily with only this one sensor, without relying on any other sensor, more complicated sensors like LiDAR or whatever. The system, we developed a system that, just like how humans do, it can autonomously navigate an environment by memorizing which places it has already visited before. Therefore, it doesn't require too much more revisiting so that it can spend more time on the unexplored, non-familiar regions. And we were able to train this whole system in a simulated environment and then deploy it in a completely different real-world environment. On this slide, on this animation, you're seeing an actual real-world deployment in our university building. So I will again skip the technical details how we achieve this. Again, the key is to develop a neural network architecture that address both the high-level task planning and also the low-level motion planning through imitation learning, so that it imitates some kind of like oracle experts to perform this task and eventually be able to autonomously explore the environment. I want to highlight a recent work called City Walker from my group this year, published at CVPR. It's called using web scale videos for urban navigation. And we believe if we're able to resolve the urban navigation problems, such as navigating a robo-dog, say from NYU to Columbia, without any human attendance, but by just relying on all the information available to a general human being, like a cell phone and Google Map, then we should be able to bring, it is easier for us to bring a robot to a construction job site, because many of the problems that you encounter in an urban navigation will be similar to a construction site. You face dynamic environment, you face dense traffic, you face different construction conditions, right? But the key of such kind of embodied AI is always the data. Where do you get the data? We never had a large enough of RoboDog navigation recordings that is available to researchers or to anyone in the company. And what we are able to do is we say we can leverage the thousands hours of videos people posted on YouTube that either includes human walking, holding a camera walking on different kinds of cities, or driving in different kinds of cities. So we curate this over 2,000 hours of YouTube videos that shows very different, very dynamic situations at different season and weather conditions. And then we're able to develop scalable AI systems that can consume this data and learn all the sort of like implicitly all the rules that humans follow either walking or driving in those environments. And then, very interestingly, we're able to discover the scaling law. So without changing the neural network architecture, by just increasing the number of training data from a couple hundred hours to a couple thousand hours, we notice the error, the error decrease, or basically performance increase, which shows this scaling law. And we also show that by including different modality, we also improve the performance. So even if your task is to walk, but if you have watched enough driving videos, it will help you walking as well. So these are all very interesting discoveries. So let me see. I want to really skip some of these later slides. This really shows our works on using AI to teach robots how to do things without requiring the human to ever know robot programming. So we essentially using a vision language model to translate a video into a robot code that makes robot programming easier. And we think this is important for industries like construction and manufacturing, so that we don't really require robotics experts to program things for us. And this is one of our early demonstrations, making keywords. And we also are aware of the human-robot collaboration which is also increasingly discussed in construction, where human workers are working with exoskeletons. You wear this kind of exoskeleton robots, and it can provide assistance to you. But the key challenge here is how to make these robots smart enough so they can understand the human intention. So here we demonstrate a capability through our own dataset and AI trained on that dataset. We're able to enable such a robot arm to collaborate with this human to predict where the human's hand is reaching out to within 1 second in advance to this pick and place operation. Right. So this 1 second advancement is very, very important because robots need time to execute its actions. And we need to do this in a proactive manner instead of a passive observation manner. So we're able to do this with reasonable accuracy that can enable better human-robot collaboration. And this is the collaborative 3D printing that I have already explained before, so I'll skip. This is the autonomous terrain grading. Again, yeah, and also the collaborative perception idea that I've explained, and I'll skip those technical details. So let me bring you to the end of my talk. So basically, there are so many open problems in the embodied AI or embodied spatial intelligence. I list some of those, such as lifelong learning, learning under uncertainty, and energy efficiency, so on and so forth, safety. In the end, why does this matter? Well, we believe the embodied spatial intelligence powers the future. It's very, very important for construction, automation, and robotics to really work instead of building ad hoc solutions. The theoretical or the fundamental science needs to be done in order to enable that future. And here I show one example, which is a translational research, or basically a startup spin-off from my lab that exemplifies this vision. So this is a student startup company called Building Diagnostic Robotics, where we build this robotic system that take all kinds of sensors like LiDAR, camera, radar, to scan building rooftops like a Roomba, as you see in this video. And then it is able to produce a line-by-line scan and with the AI-based classification of moisture damage on the rooftop. Of course, you can also repurpose this for rebar detection, which is also another service that this company is offering right now. And the cool thing is this whole thing is done very efficiently. Within 24 hours or 48 hours of a scan, we can produce the entire report to engineers. And the scanning itself is very efficient. Typically within 2 hours, 1 or 2 hours, depends on the size of a commercial building's rooftop, we can finish the scan fully autonomously, right? And then you get this kind of like a rooftop moisture map. So with that, I will stop it here. And I would like to thank all my students and collaborators and funding agencies without whom all these cannot be achieved. And I really want to highlight some of our great students that get all kinds of prestigious scholarships or fellowships, and is having the courage to take those research into real world startups and our industry collaborators. With that, I'll stop it here, and happy to answer any questions that the audience may have. Thank you.